Studying until Omniman turns me into his pet. Let's watch
The
this
angular
video
velocity
one
is the
more
overview is
time,
simple
boy.
to represent, right? Understand that?
Oh, yeah.
Okay, the formula that is the angular velocity equal the change in the angle, right, over the t, right? Okay, if you rotate one circle, okay, and the angle is the 2 pi, right? Okay, and the period is the 15 second, right? Okay, no problem.
Yeah.
This formula, one mark, another is another mark. Look at this. To calculate the time, this one, the 3 marks.
This into radians. As this goes, x passes p, and then y passes p. So this passes first, and then this has to go through 250 degrees. So we have the angle, and then we have the angular velocity. So we just put that together, and we get the time.
How to calculate the mark? This one, then 1 mark, and this one, 1 mark, and the final answer 1 mark. Okay, no problem. Okay, the topic you didn't write.
I didn't learn it yet.
Oh, yeah, this question is really about the particle physics that we have not learned yet. So this question that you finished yesterday, the first question 11, and
F equals BQV, magnetic flux density, charge, and velocity. Force, magnetic force. Alpha particles moving at right angles to a uniform magnetic field in a vacuum. Calculate the magnetic flux density of the uniform magnetic field. The force is this, speed is this, and charge would be 1.6 times 10 to the power negative 19. What does he have? He has 3 things down there. So we just have to move the magnetic flux density here, put the charge under the force, plug in the numbers, and we get it. And magnetic flux density is Tesla. Magnetic flux is Weber. A wire carries a current of 0.12 amp. The wire is placed in a uniform magnetic field of flux density 0.075. The angle between the wire and the direction of the magnetic field is 40 degrees as shown. So we're trying to find the component that is perpendicular to the magnetic flux. The length of the wire of the field is 4.6 centimeters. Which of the following expressions give the force in newtons of the wire? So force equals BIL sine theta. We're finding sine theta because we want to find, so the angle is between the wire and the magnetic flux. We're trying to find the length of the wire perpendicular to the magnetic flux. So we're doing sine theta. Length, we have current, and we have magnetic flux. So magnetic flux density is 0.75. We have amps of 0.12, and we have a length of 4.6 centimeters, so 0.046 meters times sine 40 degrees.
And I need you to help me to review what we have learned in magnetic yesterday, the chapter. What do we have learned yesterday about the magnetic field?
Magnetic flux density. Magnetic.
Anything else?
What?
I mean, the magnetic flux is what? How to calculate the magnetic flux?
Magnetic flux density times the perpendicular area.
Okay, and how about the linkage? The flux linkage?
Times the number of
times
turns of coil.
Times N. Okay, the N is what?
The number of
the coil number, right?
Yeah.
the coil number. Okay, and the force. Okay, in the magnetic force, how many magnetic force that we learned yesterday?
Magnetic force
Mhm.
is depending on whether it's charged particle or current.
Okay, for charged particle, the formula is
BQV,
okay. The Q is what?
charge.
The charge. Okay, no problem. And the B is what?
The magnetic flux density,
Yes, no problem. Okay, how about the carbon carrying wire?
BIL.
The BI. Okay, no problem. And the L is what?
L is length.
L is the length, right?
Yeah.
Okay. But here's the problem. If the right now the length is not perpendicular to the B or not perpendicular to the I, so how do we do? How do we do?
Sine theta.
Okay, no problem. To make the vertical component, right?
Yeah, find the perpendicular component.
Okay, no problem. And and I just said that yesterday, if the charged particle that will do the motion, what is the motion if the charged particle in the magnetic field? What is the motion like? The charged particle in the magnetic field.
Circular motion.
Okay, no problem. Okay, when it comes to mention the circular motion, okay, and the circular motion that will provide you the centripetal force, right? Understand that?
Yeah.
Okay, the centripetal force in the magnetic, that is called the magnetic force, okay? And let's review what is the centripetal force formula. Still remember?
I forgot.
Okay, and the centripetal force is related by three formula. The first formula is related by linear velocity and or the angular velocity or the period, right? Okay, the centripetal force. If one object to the centripetal force, okay, like the circle motion, okay, and the centripetal force is perverse to the center, O, right?
Yeah.
And the force, the magnitude of the force equal, and the m times v squared over the radius, right? Or the m, the mass of the mass of object, the mass, and omega squared
W
and times radius,
squared
radius
R.
r. Understand? Or that we use the m 4 pi squared and times r over g squared. Okay, the three formula. Understand it? The centripetal force.
I do not understand the other two.
Understand that?
Kind of forgot how to do the formula.
Okay, if one object that we do centripetal force, that we need some force to provide the centripetal force. Okay, if in the magnetic field, okay, the charged particle in the magnetic field, the magnetic force will provide the centripetal force. Okay, so in magnetic, so in the magnetic field, the magnetic force will provide the centripetal force. Okay, centripetal force. Understand that?
Yeah.
And for charged particle, the magnetic force that is PQV, right? PQV,
In the
right?
magnetic
PQV, right?
field, the magnetic force
Yeah,
will
yeah,
provide the
magnetic force that
centripetal
provides the
force.
centripetal. So the magnetic force equal the centripetal force. Okay, and the centripetal force equal what? The first mv squared over radius. Understand that? Or second, the m omega squared and times radius. Or that we use the m 4 pi squared and r over t squared. Understand that?
What is T?
Yeah, it's a t. T is the period. T is the period.
Oh, okay.
Circle motion. T is the period. The time. Understand that? If we do one counter circle, okay, the t is the period. Then we do one counter circle. The consuming time, right? The time. Understand it?
Okay.
Okay. And the v. Okay, I will try and interpret every symbol. The v is the velocity. That we call linear velocity. Like this one. Okay. The every tangent point, right? The velocity. Understand it?
Yeah.
Okay. And this symbol, the omega, is the angular. That you calculated in the last topic. The angular velocity. Okay. And the t is the period. The period is to the circle motion, one constant revolution. The time represents the period. Okay. Understand it?
What is the angular velocity?
Okay, the angular velocity equal the rate change of the angle. If we just from this one to this one, okay, the angle that we change of the delta theta. Understand that? The
Oh,
rate
okay.
that over delta t. So we got the omega. The omega represents the angular velocity. Okay, it's the rate change of the angle. Understand? The rate of change of angle. Understand it now? Okay.
Okay.
Okay. That if we find the topic, there's the charged particle that do the motion in the magnetic field. Okay, and the magnetic force will provide the centripetal force. Okay, that we use this formula. Choose one of them. Okay, understand that? Which one? Okay, understand that?
Okay, yeah, understand.
Okay, so if I want to use the equation to calculate the radius, okay, the radius, the charged particle do the circle motion, the radius of the circle motion. Okay, so we always use this one. The BQV equal the m v squared, okay, over the r, right? And I will separate the variable, and so r equal what?
So far, I understand everything, which is a good thing, but we have to go in all the way until 10:15, which is gonna be a lot. It's gonna be a lot.
Use the equation to solve
MV
R.
over BQ.
Okay, no problem. The m the product, right, and the BQ, right? Understand that? So we found that if I keep the mass and the Q, right, mass and Q, and the density constant, now the radius is only dependent on the velocity, right? Understand that? If I keep the mass, the charge quantity, and the density constant is, right? If I keep the three variable kept constant, and we found that the radius is only dependent on the velocity, right? Understand now? any problem?
No, no problem.
Any problem?
Oh no.
Okay, no problem. Okay, so we always use this formula to calculate the radius if the charge particle do the circle motion. Okay, no problem. Okay. And look at it. The yesterday never have another the Fleming's left hand rule for to distinguish the direction of the force or the density direction or the current direction. Okay, and I need you to tell me how to use the Fleming's left hand rule to help us to distinguish the direction or the force, the density, or the current. Okay, still remember?
Depends on whether the magnetic field is going into or out of the paper.
Okay. So which finger that we use to represent the density?
The index.
The index. And which finger that we use to distinguish the current direction?
Current is the middle finger.
Okay, no problem. Okay, so we have to remember Fleming's left-hand rule is previously used to distinguish or determine the direction of the magnetic force on a moving charged particle. Okay, or that we always use the Fleming left hand to distinguish the current carrying conductor in the magnetic field. Okay, no problem.
Yeah, no problem.
And look at our example. There's the current flows perpendicular. Okay, the current flows perpendicular to a uniform magnetic field as known in the diagram below. As a result, the current carrying the conductor, okay, the conductor carrying the current experiences a magnetic force. Okay, the topic want us to determine the direction of the current flowing in the conductor. Okay, how to determine? Okay, how to determine? Combine with the knowledge that we use.
Force is downwards and magnetic field is into the paper.
Interface. Yes. Okay.
So the current is going to the left.
The current is going to the left, right? From the left hand. Okay. Just like this, right?
Yeah.
Okay. So we use the Fleming's left hand to distinguish, right? No problem.
Yeah, no.
And look at okay. After we have learned the three terminologies about the charge particle, the current carrying conductor, and the flux linkage and the density. Okay. So today we're going to learn the more about the electric field. It's about the magnetic induction. Okay. The word induction there will be inducted in the environment. Okay. Which means they will produce the alternating current. Okay. They will produce in the magnetic field. And induction, they will produce the alternating current. Okay. The AC current. Understand that? Okay. And
Okay.
electromagnetic induction is a phenomenon. It's like it always occur when the EMF induced when the conductor moves through the magnetic field, or like current, or like cuts the field line, right? Or cuts the field line. Okay. So if there's a change in the magnetic flux, okay, the change in the magnetic flux or magnetic flux linkage, right? And that will do the mechanical work from moving the conductor in the field is transformed into the electrical energy. Okay, so there's the energy transfer from mechanical energy transfer into the electrical energy. Understand the process? Okay, so in the process that will induce the A alternating current or alternating the EMF. Okay, the induce the EMF, and that will do the mechanical magnetic flux. Okay, the change in or cast the field line. Okay,
Electromagnetic induction is a phenomenon which occurs when an EMF is induced when a conductor moves through the magnetic field or cuts the field line.
if there's a change in the magnetic flux, okay, the change in the magnetic flux or magnetic flux linkage, right? And that will do the mechanical work from moving the conductor in the field is transformed into the electrical energy. Okay, so there's the energy transfer from mechanical energy transfer into the electrical energy. Understand the process? Okay, so in the process that will induce the A alternating current or alternating the EMF. Okay, the EMF that will be induced, right?
Yeah.
Understand that? Okay, so this is the process energy transferring. Okay, and therefore if touch the accountable circuit, okay, if I touch the accountable circuit, the current will be induced in the conductor. Okay, so if there's the closed circuit, the current will be induced. Okay, but if there's no closed circuit, but there's the induced EMF, right? Still
Okay,
induced
got
EMF.
it.
Understand that? Right?
Okay, yeah.
Maybe I should take some notes to remember. Electromagnetic induction is a phenomenon which occurs when an EMF is induced when a conductor moves through the magnetic field. Electromagnetic induction Electromagnetic induction is a phenomenon that occurs when an EMF is induced when a conductor is moved through a magnetic field. Electromagnetic induction is a phenomenon that occurs when an EMF is induced when a conductor moves through a magnetic field. Electromagnetic induction is a phenomenon that occurs when an EMF is induced when a conductor moves through a magnetic field. If there is a change in magnetic flux or flux density, flux linkage, the mechanical work is converted into electrical energy. Therefore, if attached to a complete circuit, a current will be induced in the conductor. If attached to a complete circuit, a current will be induced in the conductor. This is known as electromagnetic induction and is defined as the process in which an EMF is induced in a closed circuit due to changes in magnetic flux linkage. The process in which EMF is induced in a closed circuit due to changes in magnetic flux. Electromagnetic induction is the process in which an EMF is induced due to the changes in magnetic flux in a closed circuit. The process in which EMF is induced in a closed circuit due to the changes in magnetic flux or flux linkage. This can occur either when a conductor cuts through a magnetic field, or the magnetic flux linkage through a coil changes, becomes more dense or less dense, or changes direction. This can occur when conductor cuts through magnetic field or a change in flux linkage happens.
Okay, and this phenomenon we call it electromagnetic induction. Okay, so remember the definition. The electromagnetic induction is a process. The EMF is induced in the closed circuit. Okay, if we want to produce the current, there must be a closed circuit. Okay, but if there's no closed circuit, the EMF is still induced, right? But there's no current induced. Understand it?
Wait, no current?
What?
What? You said no current is induced?
If there's no closed circuit, there's no current induced, right?
Oh, yeah, yeah.
No close. There's no closed circuit. There's no current induced. Okay, and there's no closed circuit, but still EMF induced, right? Understand that?
Right, okay.
No problem. Okay, and so this is also occur either when a conductor cuts through the magnetic field, right? Equal cuts the field line, right? Or cuts the field line, right? Understand that?
Yeah, okay.
The field line or cuts the field line, right? Okay. Or the magnetic flux linkage through the coil change. Okay, there's a coil change. Like for example, becomes more dense or dense, right? If there's a change in the magnetic flux, okay, then there will be EMF induced, right? Okay, and if I further have a
Yeah, okay.
the field or cuts the field line, right? Understand that?
Yeah, okay.
The field line or cuts the field line, right? Okay. Or the magnetic flux linkage through the coil change. Okay, there's a coil change. Like for example, becomes more dense or dense, right? If there's a change in the magnetic flux, okay, then there will be EMF induced, right? Okay, and if I further have a closed circuit and there's the current induced, right? Okay. Okay, and the usage for the electromagnetic induction is always used in a electrical generator. Okay, electric generator, that is to convert mechanical energy into the electrical energy. Okay, and the transformer. Okay, the transformer which are used in the electrical power transmission. No problem. Understand?
What is a transformer?
Okay, transformer is the tool. It's the tool that we always use in the electrical power transmission. Okay, it's the tool. The tool. The way if I want to transmit the electrical energy in the long distance, right? The way use transformer to transfer the electrical energy. Understand?
So it's for long distance.
Yeah, for long distance, they will always use a transformer to transfer in the electrical energy for long distance. Okay, and this formula can easily be demonstrated with magnet and the coil or the wire and the two magnets. Okay, look at the equipment. Okay, here's the magnets. Okay, and then we'll go through in the coil. Okay, there's the N, right? The N coil, right? And when the magnets and cross the coil, right? And we will see the reading, the change, right? The change in the voltmeter, right?
Yeah.
Understand the structure in the voltmeter. Okay. So when the coil is connected to a sensitive voltmeter, okay, the sensitive voltmeter, if there is any little volt changes, they'll have the deflection. A bar magnets can be moved in and out of the coil to induce an EMF in the coil, right?
Yeah.
Understand? Okay. Look at the observation. Okay, and I will narrow. Okay, look at the observation. Okay, the first, if I take the bar magnets, it's not moving. If not moving, the voltmeter shows there's a reading. Why? Because there's no EMF induced. Because there's no rate of change of flux, right? Understand that?
Yeah.
Because the bar magnet is not moving. Not moving means there's no rate of change of the flux. Okay, so when no rate of change of the flux, which means there's no EMF induced. Okay, understand that?
Okay.
Okay, and if I take the bar magnets, begin to move inside the coil, there's the reading on the voltmeter. As the bar magnets moves, okay, its magnetic field lines, okay, that will cut through the coil, right? And when the magnetic field lines be cutted, right, in the coil, that will generate a change in the magnetic flux. Understand that?
Wait, what does it mean? The magnetic field line cuts through the coil.
Yeah.
Wait, what does it mean?
Oh, you mean the cut field, which means there's a change. There's a change in the magnetic field, the lines. Understand? Cut through the coil, the magnetic field lines, which means if there's a change in the magnetic field lines, change, right?
Yeah.
Like if I dress, and we know that the magnetic field lines is from this one, right? Like this, right? Understand that?
Yeah.
Okay, so when the bar magnet moves into the coil, right? And there's a change in the magnetic field lines, right? Okay, the density will change, right? Understand that? And we call the change is cut through the coil, right? Understand that?
Okay.
Okay, and then we use the word to cut through. Okay, so if there's a change in the magnetic flux, okay, and there will be EMF induced, right, in the coil. Understand? So we can see the reading or the deflection in the voltmeter. Understand that?
Yeah.
Okay, and after that, if I take the bar magnets to take back off the coil, and the EMF is induced in the opposite direction, okay, and I will find the phenomena when the bar magnet is taking back out of the coil, and EMF is induced in the opposite direction, okay, and so as the magnets change direction, the direction of the current changes. Understand?
Yeah. Yeah.
Okay, and the voltmeter will momentarily show the reading on the opposite side. Okay, so
Okay.
If I increase the speed of the magnets induced, the EMF with the higher magnitude. Understand that?
Yeah. Yeah.
Okay, as the speed of the magnet increases, so the rate of change of flux increases. Okay, the speed is higher, so the higher is the rate of the change of flux. Understand that?
Yeah.
Okay, and make a conclusion. Here's the conclusion. The conclusion is that the direction of the electrical current and the EMF induced in the conductor is such that it is the opposed change in the produced state. Okay, this conclusion. Understand it? This is the conclusion that we will learn from the equivalent. The direction of
The direction of the electric current and the EMF induced in the conductor is such that it opposes the change that produces it. I
electrical
understand that
current
now.
and the EMF induced in the conductor is the opposite change that produces it. Understand?
It's a bit hard to understand.
What?
A bit hard to understand this one.
You don't understand this one?
Not really.
Okay, which means when the bar magnets, is taken out of the coil and the EMF in the opposite direction. Why? Because the induced EMF or induced current, the direction is always opposite direction. It's always opposite direction of the rate of change of flux. Understand that? So they have the opposite direction. Understand it? This is a law called the law. This is a law called Faraday's law. Okay. This is a phenomenon that we found. So we combine it from lambda. So we take the conclusion. Understand it?
Okay.
Okay. So you remember the direction of electric current or the EMF induced in the conductor is such that it opposes the change that produces it. Understand it?
Okay.
And look at this one. Okay, the factors. Okay, the factors. Okay, so then we are to make a conclusion that the factors that will increase the induced EMF are the first one. Okay, the first one, moving the magnets faster through the coil, right?
Yeah.
Understand? If the magnets move faster through the coil, okay, then the EMF is bigger. Okay, Understand?
Yeah.
And the second factor is if I add more terms to the coil, okay, and the EMF will bigger, okay. And the third factor, if I increase the strength of the bar magnets, which means increase the B, right? Okay, increase the B. Okay, if I increase the strength of
What
the bar
about
magnets, which is
increasing the
increase
surface
the
area?
density, right? Understand that?
Yeah,
If
understand.
if I change the will increase the strength of the bar magnets. That is the change the density, the bigger, okay, and the induced EMF are bigger, okay, EMF induced
NBA over T.
bigger. Understand it? Okay, now, right?
Yeah.
Okay, look at the rotating coil. Okay, here's the rotating coil. Okay, the equipment. Okay, to represent the A, represent the terms, and represent the B. Okay, in the rotating coil equipment, when the coil
I'm gonna
rotates,
take a break. In the rotating coil equipment, when the coil rotates. When a coil rotates in a uniform magnetic field, the magnetic flux through the coil will vary as it rotates. When a coil rotates in a uniform magnetic field, the magnetic flux through the coil will vary as it rotates. In the rotating coil equipment, when a coil, my comprehension is really burnt out right now. Rotating coils. When a coil rotates in a uniform magnetic field, the magnetic flux through the coil will vary as it rotates. Therefore, since the flux linkage through the coil also varies, this will induce an EMF that also varies. Since the flux linkage through the coil also varies, this will induce an EMF that also varies. The maximum EMF when the coil cuts through the most field lines. The varying EMF induced is called an alternating current. I think I get it now. The varying EMF induced is called the alternating current. I get it now. The varying EMF induced is called an alternating voltage. Because it's perpendicular, the motion is parallel with the field lines, so it's not cutting through any field lines, so there's no magnetic flux density. There's a minimum EMF induced, minimum change in magnetic flux linkage. Cuts through the field lines when it is parallel with the field lines because the motion of it is perpendicular to the field lines, which induces the maximum EMF because it's cutting through the maximum amount of field lines, which produces the maximum change in magnetic flux linkage. The maximum EMF is when the coil cuts through the most field lines. The flux linkage through the coil also varies. It varies throughout the angle changes. It varies as it changes. And the EMF is only induced during the movement of the magnetic flux change. So during the movement, the magnetic flux density, the magnetic flux linkage changes.
Okay, if I put in a uniform magnetic field, okay, the constant B, and the magnetic flux through the coil, the will vary as they rotate, right? Okay, understand this one. The will change, right, as it rotates. Okay, the flux, right, because the flux is the B times A, right? Understand that the B is constant. If I change the area, right?
Yeah.
If I change the area, okay, and the flux will changes, right?
Yeah.
Okay, and therefore, since the flux linkage through the coil that varies, so the induced EMF that also varies. Okay, and combine this phenomena that will make a conclusion. The conclusion is the formula. And if I want to get the maximum EMF is the time when the coil cuts through the most field lines. Cuts through the most, which means the all of the field lines across in the area. Okay, like this one. Understand that?
Right.
All of the field lines all cross through the cross sectional. Okay, right now. So and right now we have the maximum EMF. Okay, here's the maximum EMF, right? Understand that?
Yeah.
Okay, and the change, right? So if I want to get the minimum when the rate change of is zero, the rate change of zero. Okay, if the initial and the final is same, there's no change, right? When there's no change flux, okay. When there's no change flux, okay, and there's no EMF induced, okay. If there's a big maximum change, right, from the zero to the maximum, the change, okay. So we got the maximum EMF induced, right? Understand it?
Yeah.
Okay, look at it. Okay, I'll highlight it. Even though the flux linkage through the coil is maximum when the theta is zero, and the change in the flux linkage is minimal as the coil rotates, so the induced EMF is minimal because the opposite is true when the theta is 90. Okay, understand it?
Even though the flux linkage through the coil is maximum when theta equals 0. the change in flux linkage is minimal as the coil rotates. The flux linkage through this coil is maximum. The change in flux linkage is minimal. Why is the flux linkage through the coil maximum? So what he was saying when he was coloring the area, when he was coloring this, he was saying that the flux linkage through the coil is maximum. But the change, because it's parallel, the movement is parallel with the field lines, the change is minimal as the coil rotates. So the induced EMF is minimum. The movement of the coil is parallel with the magnetic field lines, so the change in magnetic flux linkage is minimal. So the induced EMF is minimum. The opposite is true when theta equals 90, when there is a minimal amount of flux linkage through the coil, but because the motion is perpendicular as the coil rotates as 90 degrees, it is a maximum magnetic flux linkage change. Increasing the coil's frequency of rotation increases the frequency of the alternating voltage and the amplitude of the alternating voltage, because by increasing the frequency you increase the velocity, the angular velocity, which increases the amplitude of the alternating voltage.
Okay. And if I increase the coil frequency, okay, increase the coil frequency of the rotating. Okay, if I move faster, right, the rotate faster, okay, the increase the frequency, the result is increase the faster, and the frequency of the alternating voltage and the amplitude voltage, right, will also be increased, right? The two. Understand that? Mm-hmm.
Wait, why the amplitude?
The amplitude, okay, the amplitude, which means the maximum value. The amplitude is the maximum value. The maximum value of the EMF induced. Understand that? Okay, the amplitude represents the big value, the maximum value, like the sine. Okay, like the sine value, right? The maximum is this one, and we call the maximum value is the amplitude. Okay, and the induced EMF, okay, the EMF induced that will change, right? And the maximum value of the EMF we call the amplitude of the alternating voltage, right? Understand that? It refers to the value of the point. Okay, EMF.
But why is it if the frequency of rotation increase, amplitude increase?
Okay, because if you improve the frequency, okay, the frequency of rotating, and will increase the speed, right?
Yeah.
They rotate faster. Okay, if you rotate faster, the rate of change of is bigger, right? Rate of change of flux is bigger, right?
Right.
Rate of change of flux density of flux linkage is bigger.
Right? The rate change of flux more, okay, the more of the induced EMF, right? Understand that?
Okay, I understand.
So they have the relationship like this, right? If I increase the frequency of the rotating, okay, or the rotation, that will increase the rate of change of flux. Okay, the rate of change of flux increases, so the value will increase, right? Understand that? And the maximum value referred to the amplitude, right? The maximum value referred to the amplitude of the alternating current also increases, right? Understand now?
Yeah.
Okay, and look at it. Okay, this is the equivalent transformer. This is the tool of the transformer. Okay, look at it.
I'm gonna take a break for transformer.
In the induced EMF between the linked coil, okay, here's the linked coil, okay, the primary coil and the secondary coil. Okay, look at that. EMF can be induced in the coil when there's the change of the current in another coil linked with the coil, and this tool we always call it transformer. Okay, understand now? So now you know what is the transformer, like this.
Yeah.
Understand? Okay, and the transformer consists with the three parts. The first part is the primary coil. Okay, the left side is the. Understand it?
Yeah.
Okay, and in the primary and secondary coils are wound around the soft iron coils. Why we choose the soft iron? Because it can be easily be magnetized or demagnetized, right? Understand it? Okay, that's the reason why we choose the soft iron to the third part in the transformer. Okay, so a transformer is made up with the three parts. The first part is the primary coil, and the second is the secondary coil, and the final one is the iron. The iron is the soft iron. Because why we choose the soft iron is the reason is it can be easily be magnetized or demagnetized, right?
Yeah.
Okay, that is, and this is the process that we produce the alternating current or alternating the EMF. Okay, look at this one. In the primary coil, look at the process that we produce the EMF. In the primary coil, alternating current produced an alternating voltage, right, is applied because it creates the alternating magnetic field inside, right, inside of the iron core, right. Therefore, a changing flux linkage, right, produces. Understand that?
Yeah.
Okay, and a changing magnetic field passes through to the secondary coil through the iron core, and the result is a changing magnetic flux linkage in the secondary coil, and the form, right, from the according to the Faraday's law. Okay, the Faraday's law.
In the primary coil, an alternating current producing an alternating voltage is applied. This creates an alternating magnetic field inside the iron core, and therefore a changing magnetic flux linkage. A changing magnetic flux linkage. A changing magnetic field passes through the secondary coil through the iron core, and this results in a changing magnetic flux linkage in the secondary coil, and from Faraday's law, an EMF is induced. Changing magnetic field passes through the secondary coil through the iron core. This results in a changing magnetic flux linkage. This results in a changing magnetic flux linkage in the secondary coil. This results in a changing magnetic flux linkage in the secondary coil. Oh my god, my brain. This results in a changing magnetic flux linkage in the secondary coil, and from Faraday's law, an EMF is induced. Okay, I get it. The primary coil has an alternating current producing an alternating voltage, which creates an alternating magnetic field inside the iron core and therefore a changing magnetic flux linkage. The changing magnetic field passes through the secondary coil through an iron core. This results in a changing magnetic flux linkage in the secondary coil. Okay. So changing magnetic field in the iron core due to the alternating EMF, alternating voltage applied by the primary coil, and the secondary coil in return is induced to have an EMF, has an induced EMF. An EMF produces an alternating output voltage from the secondary coil, and the output alternating voltage is at the same frequency as the input voltage. Okay.
The Faraday's law tells us if there's the flux, the rate change of flux, okay, and there's the EMF induced, right? This is the Faraday's law. Understand that? Okay. So Faraday's law tells us if there's the rate change of flux, okay, there's the EMF is induced. Okay. And look at it. An EMF produces an alternating output voltage from the secondary coil. Okay. And the output alternating voltage is at the same frequency as the input voltage, right?
Yeah.
Understand that?
Yeah.
Okay, no problem. Okay, look at the for example. When we connect to a DC, okay, the DC is a direct current, right? DC is direct frequency as the input voltage, right?
Yeah.
Understand that?
Yeah.
Okay, no problem. Okay, look at the for example. When we connect to a DC, okay, the DC is a direct current, right? DC is a direct current, a direct current. Okay, and AC is alternating current.
Yeah.
When we connect to a DC power supply, the primary coil of the transformer becomes an electromagnet. So describe the changes which take place inside the secondary coil of the transformer when DC current in the primary coil is. Okay, there's the three. First is the switch on, A and B remains on.
Okay, 43. I'm just gonna check real quick what we learned previously. Induced EMF. Moving the magnet in and out of the towards and away from the coil, and the EMF produced induced in the conductor is such that it opposes the change that produces it.
The current in the primary coil, right? When the DC current is switched on at the beginning, the current in the primary coil increases from the 0 to the CD value, right? Understand that? Right?
Yeah.
Okay, and this creates, right? This might create a rapid change in the magnetic flux, right? In the coil of the transformer, right?
Yeah.
Okay, I will plot the transformer. Okay. Okay, this is primary. This is the secondary. Okay, right? So when the DC current, okay, when the DC current is switch on DC. Okay, and the current, okay, the current in the primary core, right? The primary core, the primary will increase, right? Understand? Will increase from 0 to CD value, right?
Yeah.
To SDO because it's a DC current, not alternating current. Okay, will rapidly. So there create. So at the beginning, they will create a rapid. Okay, so rapid changing magnetic flux, right? Understand that in transformer?
Yeah.
In the beginning, right? Induces a temporary, right? The temporary voltage, right? They will produce a temporary, not permanent or not stable. They'll produce a temporary voltage, right? Or current. In the secondary coil, right? Okay, so the induced current will only exist for a short time, right? Understand it?
Yeah.
Okay, and the current, the induced current. Okay, the induced current will only exist in the short time, right? In the short time, because there's the DC current, not AC current, right? There's not always changes. Okay, there will exist. The induced current will only exist in the short time. Okay, understand that? Until the primary current, right, becomes steady, right? Becomes steady. Understand?
Yeah.
Okay, I will summarize the process, how to describe it. Okay. At first, when the DC current is switched on, okay, the current in the primary coil, that will increase from 0 to a steady value, right? And this process will create a rapid change in magnetic flux in the core of the transformer, right? According to the Faraday's law, okay, use the Faraday's law, this changing flux passes through the secondary coil, and it will induce what? It will induce what?
Just the EMF temporarily.
The temporary voltage, right? The
Yeah.
temporary voltage or temporary current, right? Okay, in the secondary coil. And how to end? The behavior, how to end? The ending time is that the induced current will only exist for a short time, right? Until the primary current becomes steady. Understand that?
Yeah.
So we need to describe the ending time. What is the time the current will end, right? Understand that? Okay. After we have described there's the induced temporary voltage, right? And the induced current will only exist for a short time, right? Until the primary current becomes steady, right?
Yeah.
When the primary current becomes steady, okay, and the induced current will end, right? Understand? Now?
Okay, yeah.
Okay, so after I have interpreted the detailed process, okay, so you can show me how to describe the switch on when the process is switched on. Okay, how to describe the complete process.
When it's switched on, the
At the beginning,
the current reaches a steady value, and then in the process of reaching there, it produces a rapid changing magnetic flux in the transformer.
yes,
That produces a temporary EMF in the secondary coil.
yeah, no problem. Okay, and what is the time? What is that? The process will end.
When it becomes steady, when the DC current reaches its steady current, the EMF will be gone.
Yeah, no problem. Okay, no problem. Okay, and look at this. The question two, the B. When the DC current in the primary is remains on. Okay, remains on. Okay, remains on. Okay, when it remains on, what will happen? The change. The change will take place inside of the secondary coil of transformer. When the DC current in the primary coil is remains on. Remains on.
There's
Okay.
no change in magnetic flux, so
How
it
to interpret the remains on?
remains with
There's no change in magnetic flux, so there's no EMF.
Yeah, no problem. Because when the DC current in the primary coil remains on, once the DC current remains constant, the magnetic flux produced by the primary coil is constant, right? The not change, right? Okay. Because there's no change since the electromagnetic induction requires a changing magnetic flux. Okay. So there's no voltage or no current induced in the secondary coil, right? Understand that?
Yeah.
No current, no voltage. Okay. How about the last one? Switch on, switch on. If the DC current in the primary coil is switch on, okay, how to describe the process?
an opposite EMF is induced.
I think an opposite magnetic flux will be created. Opposite magnetic flux is created, and so a temporary opposite EMF is produced on the secondary coil.
Okay, no problem. Okay, so you refer to the DC current is switch off. The current in the primary coil decreases rapidly from the CD value to the other, right?
Yeah.
Okay, when we switch off, okay, from the current will change from the CD value to the other. Okay, this causes the magnetic flux in the coil to decrease rapidly. Again, by Faraday's law, this changing flux decreases. This changing flux induces a temporary voltage, right, and current in the second coil. But in the keyword is the opposite direction, right? It's the opposite direction you have mentioned. Understand that?
Yeah.
To the voltage induced when the current switch on. Okay, no problem. And look at it. Look at the example tip. Okay, when we explain the link, every time we explain the link in the EM, both side of the coil in the transformer are very common exam question. Okay, the first we have to mention the induced EMF, okay, or the induced current, right? Induced current, okay, or we can use some terminology like the Faraday's law, right? Understand that? Okay, no problem.
No problem.
Okay, so after we have learned the law related about the Faraday's law, okay, and let me explain the Lenz law. Okay, Lenz law is help us to explain why the direction is opposite. Okay, the Lenz law is always used to predict the direction of the induced EMF in the coil or wire. Okay, the Lenz law is the induced EMF is set up in the
17 more minutes of this shit.
okay, the opposed highlight. Okay, the opposed change coordinate, right? Understand it? So this is called the Lenz law, right? So the Lenz law is always used to explain the direction of the induced EMF, right? Used to explain the direction, right? Understand it? Okay, no problem. Mm-hmm. You got any problem about the Lenz law?
No.
What?
I said no. The microphone is quiet.
Okay, so now you understand the Lenz law?
Yeah.
Or not? Okay,
Understand.
no problem. The Lenz law is always used to predict the direction, right? Okay, this is the usage. Okay. Look at the experimental evidence for Lenz law. Okay, and so to verify Lenz law, the only apparatus needed is after the graph. Okay, they will need a bar magnet and a coil of wire, a sensitive ammeter. Okay, a seal is not required. Okay, look at it. When the current diffraction, there's the induced current, right? When there is the diffraction in the ammeter, right? There's the induced current, right? Okay, according to the diffraction so we use the diffraction of the ammeter to distinguish either induced EMF or not, right? Okay, and we use the magnets, the direction of the induced field oppose the direction the bar magnet is moving, right? Okay, when the magnet is moving into the coil, right? Into the coil, okay, they will produce at the beginning, okay, at this point, they will produce the current, right? Induced current, right? Okay, and when the magnet is leave out of the coil, they will leave, and it's also the phenomenon, the induced EMF, the induced current, right? The induced current, the diffraction of the ammeter, right? In the ammeter, understand that? No problem.
Yeah, no problem.
Okay, look at it. A lone pole, either loss source of the bar magnet, is pushed into the coil, right? Because this induced EMF in the coil, right? The induced EMF drives a current because there's the counter circuit, right? Okay, so the Lenz law indicates the direction of the EMF, and hence the current must be set up to oppose the incoming magnet, right? Okay, at the beginning, right? So okay, so we'll produce the opposed direction, right? All right, opposing direction.
Yeah.
And since the lost pole approaches the coil face, the EMF must be set up to create an induced lost pole, right? And this is because the two lost poles will rebel each other, right? Understand? Right?
Understand.
Okay, no problem. And after that, the direction of the current is therefore showing in the image above. The direction of the current can be verified using the right. Okay, no problem.
That's the
Is there any problem? Which part?
grip.
What?
So tired. So tired.
The right hand grip.
Right hand grip wheel is help us to distinguish the conventional current or the pointing in the direction in the direction of the conventional, right? The current direction, right? Understand that? So now you understand the right hand grip rule now?
Understand.
Okay. So if we want to use the Lord, so we have to know one of the information. Like if you got the direction of the density, so you want to distinguish the direction of the current, okay? Or you have known the direction of the current and you want to use the information to distinguish the direction of the density, okay? So we always use the right hand grip rule, okay? As for the Fleming left hand, if we want to figure out the direction of the force, okay, so we always will choose the Fleming left hand rule. Understand that? So you know the difference between the right hand rule grip rule and the Fleming left rule. Now understand that?
Yeah.
Okay, no problem. Oh, and after that, here is the law. Okay, this law is a Faraday's law. Okay, Faraday's law to calculate the EMF. Okay, the EMF value. Okay, if we want to calculate the EMF value, so we always use this formula. Okay, the formula is what? Is the rate change of
Change
the
in
flux, right?
flux
The rate
linkage
change
over
of
time.
flux. Understand that? Okay, now, and here's the negative sign. Okay, the negative sign represents, according to Lenz's law, which says the induced EMF is set up to oppose the change coordinate. Understand that?
Okay.
Okay, no problem. Okay, so here is the law related about the Faraday's law, and another law is related about the Lenz's law. Okay, the two laws help us to explain the EMF, induced EMF value, right? Understand that? The problem?
Yeah, no problem.
Okay, so here's the and as for the Faraday's law, okay, the Faraday's law is only relate to the magnitude of induced EMF. Okay, induced EMF is directly proportional to the rate of change of magnetic flux linkage. Okay, and there's no negative, right? Okay, you must distinguish the Faraday's law and the Lenz's law. Okay, the first law is only refer to the magnitude of the flux linkage, right? The rate of change of flux. Okay, and Lenz's law is only related about the negative, right? The direction. Okay, understand? No problem. Now, okay, look at that. And then combine the Lenz's law and the Faraday's law. Okay, and the combining Lenz's law into the equation for Faraday's law is written as like this one. Okay, this one. The negative sign represents Lenz's law. This is because it shows the induced EMF is set up in the opposite direction to the opposite changing flux linkage. Okay, this equation also shows that the gradient of the graph of magnetic flux against the time, right? This is the rate change of flux, right? The rate change of flux represents the magnitude of the induced EMF, right? No problem now. Okay.
Okay.
Okay, no problem. Okay, so here is the for example. Okay, to finish the example, how to do it. The topic wants us to copy the magnitude of the average EMF induced in the coil. Okay, how to use the Faraday's law and the Lenz's law. Okay, no, not to use the Lenz's law. Only use the Faraday's law to copy the magnitude of the average EMF induced in the coil. Okay, how to do it? Think about it. How to do it? The work example have the information like a small rectangular coil contains the 350 terms of the wire. The longer side is 3.5 centimeter, and the shorter side is 1.4 centimeter. Okay, so we got the area, right?
Okay.
Okay, and the coil is held between the poles of the larger magnets so that it can rotate about and access the silver cylinder. The magnet produces a uniform magnetic field of flux density of 80 microtesla between the pole. The coil is positioned horizontally, then turned through the angle 90 degrees in the time of the 0.18 seconds. Okay, how to do it? Which formula that we use?
Use the magnetic flux formula first.
Yeah, no problem. How's
So,
the formula? This
mag-
formula, this one.
Yeah.
So, and how to copy it?
So find the magnetic flux first. So, 0.035 times 0.014 times 80 times 10 to negative 3, and then times 350.
And then the result is what? You have listed the variable, right? You have listed the lower variable, the flux, right? And the area, and the number of terms, right? And term variable.
Over
Okay, and you write
0.18.
like the Faraday's law, like this, right? This one you write it like this.
Yeah.
Okay, and take the known quantity into equation, right? Okay, into a fraction, right? Okay, and final, and then we take the known quantity into it, and finally we can get an answer. Okay, you might need a calculator to calculate the answer, right? No problem now. Understand now?
What about the 90 degrees?
90 degree. 90 degree is the angle. It's the angle, and we want to find out the flux linkage, right? The flux, right? Okay, the flux is like the change, right? The change. At the beginning, the field lines is the parallel, right? Okay, it's parallel to the coil, right? Okay, understand that? And now, and we through the angle of the 90, right? So that will become this, right? Understand that? Okay, no problem.
Okay.
Okay, so 90 degree has become the maximum area, right? Okay, so the change area, right? Just one area, right? The length times radius, right? No problem. the area, okay, the change in area, right? Because at the beginning there's no area, right? Because there's no any field lines across the area, right? At the beginning. Understand now?
Yeah.
Okay, and when we throw the angle of 90, okay, there's a maximum area, the magnetic field across it, right? Okay, so the change, right? So from the beginning to the rotation of the 90 degree, the way got the change, right? Understand now? Okay, no problem. So we calculate the area, okay, the change area. Okay, no problem. Okay, and take the long variable, the one, the quantity into the fraction, right? Understand that now?
Yeah, okay.
Okay, so this is today's physics lesson that we have learned, okay? And quick review it. And in today's lesson about the physics, okay, we have learned the length store, the Fry store, and how to calculate the process and describe the process, right? And the change of flux, right? And the equipment induced EMF between the link the coil. That is the transformer, right? Understand that?
Yeah.
No problem. And we have learned, okay, the induced EMF, okay, the every process, okay, when it change. And we have learned how to distinguish the Fleming's left hand and the right grip hand, right? Roll. Understand that?
Yeah.
No problem. Okay. So let's continue to talk about the mass. Okay, the mass. Our projection on the okay, you can see the projection.
Yeah.
Okay.
All right.
Right. Until the primary current becomes steady, right?
Yeah.
When the primary current becomes steady, got the direction of the density. So you want to distinguish the direction of the current, okay? Or you have known the direction of the current and you want to use the information to distinguish the direction of the density, okay? So we always use the right hand. And the grip rule. Okay, as for the Fleming left hand, if you want to figure out the direction of the force, okay, so we always will choose the Fleming left hand rule. Understand that? So you know the difference between the right hand rule, grip rule, and the Fleming left rule. Now, understand that?
Yeah.
Okay, no problem. Oh, and after that, here is the lower. Okay, this lower is the Faraday's law. Okay, Faraday's law to calculate.
Taking a look at how I study.
The capacitance increase.
The scalar quantity, right?
Yeah.
It is the one, the A charge, right? No problem. Okay. And the six is what? The capacitor. Okay. The six, you choose what?
I choose C.
C, right? Why C? Why do you choose C?
Because on P is the positive charge, on Q is negative charge, so it's P to Q.
Okay, no problem. Okay. And the seven, right? Seven, you choose what?
I chose B.
The answer B. Why the answer B? The answer B is right. Why the B? The decrease in the distance between the two plates increase, and the capacitance of the two parallel plates. Okay, here's the two parallel plates. Okay, just the graph, right? The same graph. Okay, because the question 6 and 7 refer to the information below. Okay, and the separation it decreased at the time x, right? So when I decrease the separation, what quantity that will change? Mm-hmm.
The capacitance increase.
And how's the current change?
I think current increases because
There's a new formula, I think. There's a new formula. There's capacitance equals current over 4 pi epsilon r squared, I think.
current increase because the charge increases.
Okay, at the initial condition, right? If I increase the separation of the two parallel plates, okay, so then we can use the formula related to the capacitance, right? The C equal the A and it's 4 pi, right? 1 over D, right? Understand this formula, right?
Yeah.
Related to capacitance. Okay, so if I decrease the separation, so I change the D, right? Okay, decrease the D. So the C that will increase, right? Okay, now the C that will increase. If the C increase, the capacitor that
Rest have to be constant. So D, there's no squared, it's only D. Oh damn. I'm gonna have to write this down. Please. Yeah, done this. I'm gonna morgue you. Oh, Q dog. Oh.
What? What?
Why are you so quiet, boy?
Hold up, I'm making dinner. Wait.
Oh, that's
Wait,
so
wait.
hot, boy.
What the hell?
Oh, yeah. My name's ES, boy. A hot husband making dinner sounds such a hot idea to me. Hey, what is wrong with you? Hey, what?
Too horrifying.
What,
Too
you couldn't handle
horrifying.
it?
I could not handle ES. Elvis is too scary. You can't just do that to me.
You do that all the time to me.
Hey, you can take it.
What? What? Is that an insult?
No, it's a compliment.
I don't think
Actually,
that's a compliment.
is that? I don't know. Is that insult or a compliment? I don't know.
I take that in offense.
Okay. Well, fuck you.
Hey, I take that in offense as well. You're offending me.
Hey, how's your studying?
It's really bad. I am dying from the burnout and the tears and sorrow.
Any blood?
Yes, blood, sweat, and tears. Oh, also, the reason why I came here was to show you, you know, like the person that you didn't trust was hot?
Yeah.
Check,
That's
check,
dot
check,
dot.
check chat.
That's dot dot.
Yeah. Do you think she's hot?
Can't see her face.
Wait, so you need to see the face to fully know?
I mean, to be fair, I don't really judge on appearance, but like, sure.
Sure. So
Yeah,
give a
I guess
comment. Give a comment on this attractiveness.
attractiveness. Uh, okay. How are we rating this? Cause I would rate a lot of things, right? Let me see. I think body wise is okay. I think let's rate it like out of 10. Body is like I guess a 7. Clothes, bad fashion, very generic. So that's a 2 for me. I can't see his face. I can only see her phone. So no points on that.
Zero out of 10 fashion, right? 2 out of 10 fashion, 0 out of 10 face.
Yeah. If I'm being honest, I don't know how to rate how attractive a person is.
Kira, goddamn, that's. Do you know what kind of score that is? That's 9 out of 30. That's 3 out of 10 in total.
I think I'm just really bad at rating. I don't know. Hold up. Let's bring someone else to rate this. Who can we ask to rate? People. You know what? Let's rate people. Not just her. Let's just find. Let's just like start rating people. I think that would be funny. We could start rating people now. Yes. People tier list. Hello. Is Chris talking?
What?
What do you mean rating people?
You
Rate
see the
rate
image
rate
Chris
rate
said?
people's attractiveness.
I
Like,
guess
by
apparently that's what we're
appearance?
doing.
Yeah.
Yeah, by appearance, I guess. Look at the image Chris sent. That is apparently dot dot. How will you rate dot dot?
How will I rate? What?
How do you rate the image in chat dot dot?
Wait. She looks basic.
Basic. Goddamn. Oh my god, you guys are harsh.
What?
That's the truth.
It's the
We're
truth.
very
Wow.
we're very serious when we're rating people.
Oh my
No.
god.
Her colors are basic. Okay.
Yeah, her colors.
I'm sorry. I rate outfits, and she's not showing her face, so it's basic.
Oh my god.
Yeah.
Alright, that's fair.
Yeah, that's true. That's very true. Let's where can we let's find a people tier list. Because apparently that's what we're doing now.
Semi. Wait, is there another photo?
I have another one.
We're rating a lot of people, right?
Let's
It's,
rate all the people.
this is definitely a different girl.
It's the same freaking door at the back. What do you mean a different girl?
No.
Yeah.
You can see the camera is blurry, so it's different.
No.
Cameras? No.
It's still basic. She just changed the top.
But now it has more texture.
I found a rating people tier list.
No thanks. I don't like it. It's basic, okay? It's basic. Too basic.
God damn,
It's
you
like
guys
it's
are...
like what those girls would wear.
What kind of
It's like
girls?
the average
The one in our class.
Oh man, oh my god. You have a hatred for them.
Yeah, average girls, yeah.
Yeah, it's just like very
I don't have a outfit for myself.
I wear very average too, but I don't know. I wear very average in summer because it's hot. But
yeah,
in
same.
winter I wear more.
I try not to, but sometimes like during summer I just don't really care and I just wear anything
Yeah.
outside. It's too hot.
Where's the tier list?
Wait. I'm sending.
Yeah.
Rate
There's
my
another
outfit.
one.
This is my outfit.
I like the turtle. Oh my god, the turtle pads.
Yeah, I like the turtle.
I
Is it
think
for protecting your butt?
Yeah, it is.
I think the turtles. I think it's like,
You should have one for your head too. Sorry.
Are you tired? You slept at 5 last night, did you not?
Yeah.
Here, let me share screen. Some of these are not people. I want to point out. I looked at it. Some of them are not even people. Some.
Some of them are drawings. Oh, never mind. Why is Gojo there? Gojo D.
Really? Okay.
He's not
What about
real.
Goku?
That's true. Goku doesn't
There's no
sign
Goku
it.
here.
Oh man.
That's right. No real.
Why is there a car character?
He's very square.
Who? First one?
Yeah. I'll rate him D.
Guys, I sent another
What
video
do you
in the
guys
chat.
think?
This is my normal fit. How do you think about it? Kira, you see me all the time in this.
Yes, I like your red jacket, to be honest. I know it's your school jacket though. Is it not?
Wait, what did you say about the blue one?
The school outfit.
No, it's not my school one.
Like
No, it's just my normal
red.
jacket.
Wait, really? I thought you had like a red.
Yeah, but that's
Oh,
thicker. That's for winter.
Oh, I see.
Your school have a red jacket?
Yeah.
That's
Is it a weird color?
that's different. That's just
find-
different.
Let me find a. Let's find a different tier list.
Oh my god, there's Niji Sanji Ian tier list.
What is that?
Niji Sanji is
Who's in
a VTuber company.
Oh, actually, yeah. Let's just do tier list. It doesn't have to be.
Rating
Oh,
them?
oh.
That's the.
You want to rate this one? I don't know what this is.
Reality TV. I'm actually not good at rating real people. I have my own preferences and stuff. No. Anime and manga. Ooh.
Hong Kong stuff as well.
Oh, Project Sekai colorful stage character tier list.
Blind Way. Oh, I played a little bit, but mine's in
Oh.
Chinese and I cannot understand it.
Yeah. Do we rate them by appearances?
Yeah, I guess so.
Okay.
First
Do
of
we
all,
like all have like a opinion ourselves and then we choose the most voted opinion?
yeah.
Okay.
Chris, go first. Chris, what do you think?
About
What do you
what?
think of Ena Shinonome? first
Which one
one.
is that? Which one is that?
The first one.
Okay, you
What do you
guys
think
do
of
that
Ena?
while I.
Very, very innocent looking.
Oh yeah. Sure. She's innocent.
Wait, really? Wait, am I wrong?
You're kind of right.
She
Okay, let me give you some descriptions. She has mild anger issues and
Oh my god.
she's an artist.
Well, what are we ranking right now?
Appearance
Oh.
from S to F, I think.
Give this a B.
B. Oh. Hmm. Let me. I don't want to be biased. I think she's an A. I like her. We need one more opinion, bro. Quentin, come back. Okay, let me dry my hair first. I chose A.
Back. I'm back. I'm back. Okay. I think. Chris said a B, right? Yeah, I think she's very innocent looking. I agree with Chris. I think I think I think a B is a
I'm back.
Hi. Hi back.
Hi. Okay, bro.
Hi back.
Well, what do you rate the first one?
I think it's like a top B. Not A yet. Right? But like top B. In my opinion.
Yep, top B. Yeah, sure. I chose
Okay, top
A.
B. Ah.
Also, Kirag,
Hmm.
you know the Indian girl that I sent in chat? She said she's in engineering, so that explains her outfit.
Ah.
I don't think engineering
What?
students dress like that.
Why? Why not?
She's gonna die.
She's gonna die? What?
Oh,
I
is
think
she? Some
I
say,
think
some do.
No, 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 no,
well, I
no.
feel
She's
like
she's another person.
Oh, okay.
We haven't
I
seen
feel
Some
like
Say Some
if
Do in so long. We should invite her to our Oh wait, I'm not gonna be gaming. This is so sad.
It's okay.
who- some say some do.
The girl we met in Neighbors.
Yeah, the one pretending to be Indian.
The one we called white.
Because she is
She's
white.
not.
Wait, no, she's Asian.
Wait, no.
But she sounds white.
What? No. What? No, what is she
We
then?
we sound white too.
No.
Okay, bro.
I do not identify
Let's
as white.
Okay.
Okay.
We'll just.
Alright, moving on.
Oh, I like the white hair.
A.
S tier, S tier.
I agree with the A.
I like the hair
Hopefully,
as well, so S tier.
I think it's A.
A.
Yeah,
Which anime is this?
maybe. This is
It's from a
Twilight
game.
Princess. It's a
Oh.
game. It's a rhythm game.
Let me look at this fat chud. She could be behind the white hair girl.
Yeah. I agree. I like her hair.
S tier, 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 S tier. Thank you. Thank
She
you.
looks
Thank you.
pretty
Thank you.
shoddy, but yeah.
Thank you.
I like her. I like the paint. I like the
Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. I love her so much. I love her so much. No Mizuki slander here.
Actually no, I think oh yeah, I just
Why
saw
is
it.
Anna B tier? we're ranking by appearance. Kaka's favorite is Anna.
Oh.
Okay, Wanami.
Okay, moving on.
B tier.
B
Yeah.
tier.
Maybe.
Why?
Really is a
Boring.
maybe?
This character looks boring. I mean, we don't get to see them in full clothes.
Yeah, we don't get to see their clothes. They should have like a full sprite. Okay.
Yeah. Hmm.
We should actually never mind. Let's not do this tier list. I'm too biased
Okay.
with everyone.
What other two? You wanna do like a
Men? Wait, what is men?
What is
men?
men?
It's just men. What do you want? It's men. You just
Is it just every single man in the world?
no, it's like anime.
Oh, you
Vegeta!
vote. Wait, you can vote. You can scroll up and vote.
Vegeta!
It's so much faster if you float.
You know the top half. Most of the people in the top half. I don't know much on the bottom half.
I know some of them. They're from Tokyo Revenge or something, and some are from Blue Lock.
I see Metal Alchemist.
Ah! Oh my god. My
I
ears.
see Metal Alchemist. And that blue lock guy. There's also Leo Rio. Leo Rio! I'm LARPing.
Which one is Rio?
They're from Hunter x Hunter. He's from Hunter x Hunter.
Oh, Hunter.
大事のすぐ閉めて君はねだめてゆく天使を微笑みて図で出して Okay, vote.
Okay, let's start. These two basketball players.
You can vote at the right side, so you don't have to drag
Yeah.
it. Who's this guy?
I have no idea. I know it's from Slam Dunk. Like the
Yeah.
basketball
I
anime.
don't like his smirk and his haircut. I don't like his haircut.
His hair. I think he's like
Let's not vote him too low. Let's
Why
go
can't we do a
C.
Gachi
I'll go
Yakuza
C.
one?
right? C? Yeah, I think C.
See,
Okay, this guy.
his haircut's a little better. So, C, but fronter than him.
Yeah.
Oh, you can't move it? It's okay lah.
Oh well. Okay.
Oh, Nanami.
No.
B.
Yeah, I would say
B.
it's a B. I think
Yeah.
he looks better without
I would
the
put him
haircut.
in A though. Because he's
Really?
cool.
Hmm.
In appearance wise, I guess B. Yeah.
Yeah. Right? His appearance is B.
D.
Mahito. Yeah, I was about to say D.
Wow. He's tan. Wait.
He,
I can't even see his hair, bruh.
no, you say 10 or 10?
Like a C again.
Yeah, I think it's a C.
See, yeah. He tops Mahito.
Oh, this
A.
is Retro
A.
One.
A.
A. This guy is from One Piece.
No,
I
trust
agree.
me. A.
Yeah, it's A. It's A.
Okay.
I love One Piece. I watch all
A.
B. B. B.
A.
B. B.
I like his eyes.
No, he's a
D. D. D.
D? No! He's not that bad.
He's not that.
I like his. I like how his hair is like affected by lightning, and his hair changed color because of lightning.
You know those like
I think it's pretty
flat
cool.
noodle snacks? His hair remind me of that.
True. Okay, C.
B.
Fine, B. Whatever. S.
F tier,
No
no notes.
way.
F tier, no notes.
No, I mean, if he wasn't, if it's like his human form, I would get it, right? Like if he was a human, right? Human form, I would say it could possibly be a S. But,
No.
like his no.
Hear me out.
Who are you talking about? Who are you talking about?
B. B.
Watch my screen. I think I know what
Anyways, why is Zenitsu a D?
I don't know.
Whatever.
Why isn't
Ever.
Oops. Actually, why did I put him at D? I forgot. I heard someone
Said,
say
we
C, I
said
just
B.
Put him
Yeah,
at
we
F.
said
B.
B.
B for boy.
Yeah.
Put him at F. We're charging, right? And the end leader, they have the current, right? Okay. Understand that? So the current will increase, right?
Okay.
The current will increase, right? Okay, no problem. So the point, the x, that have the increase, right? Okay, and the y, at the time y, the separation become constant. Okay, if the separation become constant, so the c constant, right? If the c constant and the carbon the constant, right? Understand?
Okay, yeah.
Okay, and the next, the topic is the 8, right? So you choose what?
I didn't know how to do.
Okay, look at it. The initial potential difference, okay, so we call it the V zero, right? And the capacitor is discharged. Now the capacitor is discharged through the resistor. Okay, so in the process that we are discharging, right? Discharging the energy, right? Which means the capacitor that will release the electrical energy. Okay, and the potential difference across the capacitor decrease to, okay, in 2 milliseconds. The time, so we got the time interval, right? Understand that? The time interval, the
Oh yeah.
time is what? Is what? It's
It's 2
2
millisecond.
mile 2 millisecond, right? Which means the 2 times the -3, right?
Yeah.
Okay, second. And so the potential across the capacitor decrease to, okay, what is decrease to? So the remaining potential is what? Decrease to. Mm-hmm. What is the capacitor decrease to? Decrease to without the over 3, which just means what? Mm-hmm. Means the remaining voltage, right? Remaining voltage is without over 3. Understand that?
Yeah, okay.
Okay, so which formula that we can use to calculate the time constant? Mm-hmm. which formula that we can use? Discharging, right?
Oh, okay.
Discharging formula relate to voltage, right? Okay, have you ever remember this? And the remaining voltage, right, equal what? And the initial voltage and times what? The E, the negative T over RC, right? The RC is a constant, right?
Yeah.
Understand that?
Yeah,
Okay, and here we know the remaining voltage, right, is what? Is the V double over 3, right?
Yeah.
Understand that? So we can cancel this one. So we can get the 1 over 3 equal the E negative T over RC, right? And we also know what property?
At the time.
Okay, the time interval, right? Okay, so let's take the time interval into equation, right? To solve what? To solve the RC, right? 1 over 3 and equal negative 2 times the negative 3, okay? And over RC, right? The two the known quantities that we know. Look at it. The topic, first we read the remaining, right? D equals 2, which means the remaining, okay? Understand? The D equals 2, which means that in the discharging process, and the remaining potential is what? Is this one, okay? Remaining. Okay. Understand that? And we also got the time interval, right? Okay. So we have to know the remaining potential and the time interval. Okay. And we want to get the variable time or constant. Okay. So first we have to remember this formula. This formula, discharging, right? Discharging relate to the potential. Okay, understand that?
Yeah.
And we take the known quantity into equation, right? So we got this equation, okay? And then we use the two-side law, right? Using two side law in x, right? Okay, and we also finally we got the answer, right? The one a nano flower x as the point charge at the center of the flower. At the distance, okay, we have known the distance from the center of the particular flower. The potential is a negative, okay, and the potential, okay, away from the center, the potential is the negative 16 voltage, and we want to show that the charge on the flower is negative. That's one a nano charge. Okay, and you how to do it? How to solve it?
Use two equations.
What equation?
First one is charge over 4 pi permittivity of free space times r squared, and the other is
Because the object in the topic is the charge point, right? So we want to calculate the potential, right? So we use the charge over 4 pi epsilon, right? Okay, and times what? The
r
distance,
squared.
the r, not r squared, the r.
Oh,
Not r squared, the r, okay, the formula. Okay, and to take the variable and q, so also q equal what? The v times the 4 pi, right? Epsilon and times the r, right? Okay, understand that? No problem.
yeah, yeah.
Oh, and finally we take the known quantity into equation, and the weight is negative, it's negative 6, negative 16. Okay, and times the 4 pi. Okay, and here's the epsilon. Okay, here's the epsilon is what? It's 8.85 and times the and negative 12. Oh, 12, okay, and times what? The radius. Okay, finally we can got is probably the answer is negative 1.07 times the 10 and negative 10 charge. And about the final answer approach to this one. Okay, understand that the process, the detail process. Okay, understand now. Remember this one equal this one. Okay, no problem. Okay, and how about question 2 of the B? You how to do it?
Calculate the electric field strength.
What?
Calculate the electric field strength.
Calculate. Okay, and deduce. And so we want to deduce whether the suggestion is correct. So the first thing you have to answer the question: the suggestion is correct or not. Make the conclusion first step. Understand that? First, we need to make the conclusion. Okay, so the conclusion to represent the suggestion is correct or not. Okay, so you think the suggestion is correct or not?
Is incorrect
Okay, so the incorrect. Why?
because when you calculate using the radius, you get 89.9, which is smaller than 120.
Okay, and we can use electric field strength, right? The formula, the Q over what? Over 4 pi, right? The 4 pi epsilon and times the radius square, okay? Understand at what? At what? At 10, right? At 10 centimeter, right? 10 centimeter. Okay, to copy it, right? And take the 10 centimeter into equation, right? So we got the Q over 4 pi epsilon and times transfer unit, the negative 1. Okay, the double point 1 square, okay? Understand that? The finally, we can get electric field strength at a distance, the center, the 10 centimeter, okay, is the approximately, use the calculator to calculate. And the final result approximately the 96 voltage per meter, okay? And we found the result answer and less than the 120, right? Understand that? No problem. So 5 is for the conclusion, and 1 mark for the formula, and 1 mark for the result value. Okay, it's 17. The Q1. I only just want to ask.
Okay.
Okay. And the okay, so like the electric field. And
The experience of force.
okay, so what person force, right? The electric force, right? No problem.
Yeah.
Okay, no problem. Here's the answer divided into the first one. If your answer relates to the electric force, so we can get 1 mark. Okay. And another mark is for the static charge. Okay, because static is the electric field. Okay, understand that now.
Okay.
Okay. And the next question is 17, right? Okay, it's 17. The Q1. I only just want to ask the Q8, right? Okay.
So 5 hours of studying total today. Ah. 5 hours of studying today. I'm gonna continue tomorrow. Hopefully starting at 12 and ending at 12, so we're gonna have a 12-hour stream.